Hello and welcome to the second lesson on the binomial distribution. Whenever you see this sign, it's meant to be a pause sign. I know it looks like an 11, it's meant to be a pause. You need to pause the video, have a go at the question or make your notes and then come back to it afterwards. So as a bit of a warm-up, I've got this question for you. So a doctor has 10 patients. It's going to be a nice red heart, there we go. Has 10 patients booked into a 1 hour slot in his practice. The chance that any single patient is late is always 0.1. I want to know, what is the probability that 2 patients are late? Pause it and have a go. So let's think about this. Obviously there are many combinations of patients being late. It could be that the first 2 are late and then the other 8 are all on time, etc. Or you might have just the first one late, next one's on time, then another one's late, and so on up to the full 10 patients. Now, if we're back from last time, we were saying that the number of combinations is represented by 10 factorial over, we've chosen that 2 are going to be late and the rest are on time, and times by the probability that they're late is 0.1. There's 2 of them, so we square it, and probability it's late is 0.8. Look, 0.9 even, and there's 8 of those. And you put it all in a calculator, you get an answer of 0.194 being the probability that there are 2 people late. Slightly trickier problem now for the same doctor. He still has 10 patients, but this time in a more sort of real life scenario for a doctor's practice, I know if 3 of my patients or more are late, then this doctor will start to fall behind. So I want to know is, what is the chance that the doctor falls behind? Basically, what's the chance that 3 or more patients are late? Now, we could view this problem as it states. Okay, the chance they are late is either that there are maybe 3 late, 4 late, 5 late, 6 late, all the way up to all 10 being late. Now that's a lot of combinations to work out, that's a lot of things, and by all means you could have gone through and done all that. But sometimes we need to look for a slightly quicker way. So instead, we're going to look at the chance that they're not late. The doctor isn't running late with his practice. So that means 2 or less are late, everyone else is on time. So you could have all 10 on time, we could have 9 on time and 1 late, or 8 on time and 2 late. These are far fewer combinations to work out by looking at the reverse scenario. So if all 10 are on time, the chance of that is 0.9 to the power of 10. The chance that only 1 is late, well, here's the number of combinations here. Probability of 1 late, 9 on time. And again, this is one from earlier, so 10 combinations, we've chosen 2 of them, 0.1 squared times 0.9 to the 8. So that should have given us 0.34867, 0.38742, and from earlier, this was 0.1937. So the probability that the doctor's practice is on time is where there are 2 patients on fewer who are late. That's all these added together, which is 0.9298. So the chance the doctor is running late is going to be the other side, so 1 minus that, which is 1 minus 0.9298, which is 0.07. Well, 7% chance that the doctor falls behind his schedule. Please note that I haven't just jumped to this line or this line. I've written out all of my workings, so you should do exactly the same as well. Right, here's some notes. So, how do you know that a distribution is binomial? Well, first of all, there's a fixed number of trials. So, for a doctor, there are 10 patients. Okay? Each trial could be a success or a failure. So, there's 10 patients, number of trials is n. Our success was actually, in this case, being late, and our failure was being on time. So, success doesn't always mean like a good thing. So, if you look at maybe like a road traffic accident, you might view success as an accident occurring, which seems counterintuitive. If you think about what you're looking for, so success is the thing you're looking for. Trials are independent, so the fact the first patient is late doesn't have any impact when the second person turns up on time or not. So each person is an independent event happening. Now the chance of success P is constant. So there's a bit of a generalized assumption here. So we're saying that every patient has a 0.1 chance of being late, no matter who they are, how far away they live, how they get to the surgery. We're ignoring all those other factors, which might seem ridiculous, but if you've got a large enough population, then the average probability of being late will work out pretty constant. So you need down those 4 key ways of working out if something's a binomial distribution. Okay, here's another example. So there are the 4 conditions. A biased coin, so you can write this down. A biased coin has a probability P of heads, or heels as that says, and Q of getting tails. If I toss a coin 4 times, what's the chance of getting 0 heads, 1 head, 2 head, 3 head, 4 heads? Okay, let's think about this quickly. So chance of 4 heads, 0 heads. So I have 4 events, and out of those, 0 heads and the rest are tails. I times that by the probability of getting heads, and there's none of them, and the probability of tails, which is Q. And there's 4 of those. Now we can simplify this, we've seen before, as 4 choose 0, so P0, Q4. Chance of 1 head, going to be there's 4 events, 1 of them is heads, times the probability of 1, and 3 of those are tails, 2 heads, so squared, Q squared, 3 heads, so 4 events, 3 are heads, probability of success, cubed, probability of failure or tails, there's only 1 of those, and then 4 heads, for that one. This may start to ring bells from C2, and your binomial expansion. So if I wanted to expand the brackets of P plus Q to the power of 4, from C2 you would have got 4, 0, P4, because the Q0 is 1, doesn't count. Then we'd have got 4, 1, P cubed, Q1, plus 4, 2, P2, Q2, plus 4, 3, P1, Q3, and 4, 4, Q4, because P to 0 is 1. So what's really nice now is you can see the link between your binomial expansion in C2 and our work in statistics, which does mean you can jump between places you want to go much faster working it out. So a generalized version of that, in a generic form, looks like this. So what's the chance that my event equals a certain number of failures or successes? So the chance I get so many successes is the number of trials, so n choose C, so n trials and x successes, times the probability of that success, the power of number of successes you get, is the chance of failure, which is 1 minus p, or you can write it as just a q, and it's going to be everything left over. So if I had 10 events and 2 successes, so the n was 10, I'd want 10 events, 2 successes, probability squared, using q for failure, and then what's left over is 8 other events. Okay, or 8 failures. You need this down as well as a generic form. So the last thing to look at is what's called a probability distribution. This just means every single potential outcome. So I want to know every potential outcome for a discrete random variable y. So discrete just means looking at whole numbers. So you could have 0 successes, 1 success, 2 success, 3 successes. You can't have like 2.5 successes, okay? Random variable, because if it's not random, then it's fixed and it just blows the whole thing apart. Okay, the probability of p and n equals 8. So quickly for the first one. All right, so there are 8 events, 0 successes, times the probability of success, there's none of those, probability of failure, and there's 8 of those. Or, for shorthand, this just comes down to q to the 8. Okay, what we need to do is to fill out the table all the way up to 8 successes. Because that would be the probability distribution, i.e. all potential outcomes from this event y. Okay, so you've got something like this. So I've used 1 minus p rather than q to the 8. Both are equally acceptable. And then these are all the potential outcomes up to 8 successes, which just boils down to p to the power of 8. We just have time for one example. So the question is, a fair 6-sided dice is rolled 5 times. What is the probability of getting exactly 2 6s? Let's double check its binomial. So, are there a fixed number of trials? Yes, there are 5 of them. So n is 5. Each trial could be a success or a failure. Good, so a success is getting a 2, and a failure is not a 2. Trials are independent. Well, it's a fair dice, okay? And the chance of success is constant, so because it's fair, the chance of success is always going to be 1 out of 6. So in answering this question, first of all, we state that it's binomial. So we're going to say, now this is how we do it. So you say x can be represented by binomial, where n is our number of trials, which is 5, and p is our chance of success, which is 1/6. We then write down our generic case, so the chance that x is number of trials, x successes, p to the x, and then the chance of failure to everything else. So in this scenario, we're not getting exactly 2 6s, so it's going to be 10 choose 2. Chance of success is 1/6. I want 2 successes. Chance of a failure, therefore, is 5/6. And so out of 5 events, not 10, out of 5 events, I want 3 failures. And remember, in a calculator, this can be written using our NCR button. So you should get an answer of 0.16123 significant figures.